I know we went over the mole briefly at the beginning of the semester, but it was pretty super brief. It was like, what is a mole? Okay, moving on. So this is a little bit more in depth. Does anybody remember what a mole is? Any ideas? An amount of a substance. Perfect. So a dozen is also an amount of a substance. So what number does a dozen represent? 12. Correct. And so a bushel is like 144. Or no, not a bushel. A gross, I think, is 144. A baker's dozen is 13. So those are just numbers of things, and instead of saying the number, they give it a name. It's the same thing with the mole, and I'll write how many things this is. It's 6.022 times 10 to the 23rd things. Correct. Yes, Hunter, that's correct. And yes, Anna, it is called Avogadro's number. So this number of things is equal to 1 mole. We talked a little bit about conversion factors in the beginning, and this can be turned into a conversion factor. So what you need to be able to do for this section, or to learn from today's lecture, is to go from grams to moles, and then grams to atoms, or molecules, or formula units. Now, when I say formula unit, a formula unit is the same as a molecule. It's just you call it a formula unit when you're talking about an ionic compound. So H2O is a molecule, and NaCl is a formula unit. That's because this one's ionic, this one's covalent. So molecule, formula unit. So you may see those words, and I just didn't want you to be like, how come they call it a molecule here and a formula unit over there? Because those kind of things, those little bitty tiny things, are the things that always bug me when I'm trying to learn something new. And I'll just get completely hung up on just that one idea and spend like 30 minutes to an hour trying to search for the answer somewhere instead of just going through. So I thought I'd let you know. All right, so I want to do some examples. So you have kind of a process. There should be a process in the regular textbook, and there should be a process in the second textbook as well, the free textbook. Before we get into those, though, I want to show you one really quick, simple thing that you need to be able to do, and it's called finding the average atomic mass. So let's take a look at that. If you look at the periodic table has an atomic mass that's something like 15.9997 for oxygen, but it's supposed to be the neutrons plus the protons, right? We don't have like a fraction of a neutron in there or a piece of a proton. So it might make you wonder, why isn't that a whole number? And the reason is because with different atoms, they have isotopes. So with carbon, there's carbon 13, carbon 12, carbon 14, and there are different amounts of each one. Now, the atomic number for carbon, and you may want to pull up a periodic table in a separate screen, just so you can refer to it from time to time. Oh my gosh, lost my cursor. Okay, there it is. Yeah, thank you, 12.01. Oops. All right, that being the case, when I say carbon 13, that means the mass of that one is 13. Carbon 12, the mass of that is 12. And the mass of carbon 14 is 14. So which one do you think there's the most of? Carbon 14, 13, or 12? carbon-12. And how can you tell that it's probably mostly carbon-12? Any ideas? Correct. It's closest to 12. So if I look at this number here, it's almost exactly 12. So it means, yeah, the mass leans heavily towards 12. So you may have a question or two that will ask you, which of these has the highest abundance? And that's not necessarily asking for the actual abundance. It's asking which one is highest. And so you know that there must be mostly this because it's close to 12. So let's take a look at another example. And I'm going to make up an example because I don't know the atomic abundances off the top of my head. So I'm going to make up something. But this is just the process and how it works. So we have element X, and I'm going to make 3 isotopes. One is going to be 14, 13, and 15. And so I'll give you the abundance. Trying to look so I can see if I can tell you what page this is on in the textbook. Come on. Okay, so if you go, well, that didn't even give me a page number. If you go to section 4.2, I believe it's page 60, at the top of the page, it's got neon. So we'll do that example. That way I'm giving you an actual atom. Come on, clear. Okay. So they're giving the atomic masses of the different neons, and then they're giving the abundance, and then they're averaging them all together. Oh, chapter 2, that's a good question. So page 60, chapter 2, section 4. And hang on one second. Okay. All right. So they've got these different ones. There's neon 20, neon 21, and neon, those should be capital N's, by the way. I don't know what I'm doing here. 22. And they give the atomic mass of each of those isotopes, which is very close to 20, 21, and 22. So for 20, I'm just going to put mass here, and then abundance beneath it. All right, so for the mass for 20, it's 19.9924, which obviously would round up to 20. And then 21 is 20.9940, and then 21.9914. The abundance for each one is 4838%, and then 0.2696%, and then 9.2465%. Let's see. There will be a couple of different ways you might be given this problem. You could be given the average atomic mass that you find on the periodic table and be told to, solve for one of the percentages, which you could do, or you could actually solve for 2 of the percentages because you could do a system of equations for that. But let me show you The abundance, that's a good question. Abundance means how much is there in the earth, but how much do they estimate is in the earth? So they would assume that, or not assume, they're estimating that neon 20 makes up most of the neon, and it would be about 90.4383%. So the procedure to do this is first you want to change all of the percentages to fractions. And when I say fractions, I don't mean like numerator denominator fraction. A lot of times they'll call it a fraction, but it's really a decimal. So what they're doing is they're just converting it to a decimal. To convert to a decimal, you divide by 100, or you just move your decimal place over 2 places. And in the paragraph above the example, you'll see they give you the percentages, and in the example, they're giving you decimals. But this is why they converted to decimals, so that they can multiply these two. So then they're going to take, and they're going to multiply those two, multiply those two, multiply those two. You're going to get 3 answers, and then you're going to add them all together. And that's going to equal your average atomic mass. When you multiply the first one for neon 20, you get 18.0898. And then for the next one, 0.05660. And then 2.03344. And then the last step is just to add those things together. When you add them together, you get 20.17992. That's a good question. So I'm multiplying the mass times the abundance. So these are the ones above that line are all the mass, and the ones below that line are all the abundance. So let me write out the formula. Anybody need a second on this page before I go to the formula? You can't find the abundance on the periodic table. That's a good question, though. And for significant figures, since you're multiplying first and then adding, first you're going to count the number of significant figures. So we can do that in each one of these. So it's 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, and then another 6, 2, 4, 6, 2, 4. And then, oh, Arib, you have a question.
So, Professor, I'm a little bit confused. I want to know, are we given the mass and the abundance in the question?
Most of the time you're given the mass and the abundance in the question. You'll be given all of the information that you need, but you may need to solve for an abundance or a mass or something like that. But you won't just be given the periodic table and be told to figure it out. So you will be given some information. And you'll see in your homework, there is an example in the homework that seems really hard, but it's, if you look through the homework guide that I put on D2L, it should help you think through it a little bit. It's not going to like solve it for you, but hopefully it'll get you kind of thinking in the right direction. And then if you need help, just let me know and I will help you out with that. All right, so let me put the formula on here. All right, the formula is mass of A. I'm going to call it A1, so that would be isotope 1, times the fraction abundance, and then mass of isotope 2 times the fraction of its abundance, And then mass of isotope 3. Now, you might not have 3 isotopes, but however many isotopes you have, you're going to multiply the mass of the isotope times its abundance, and then do that for each isotope you have, however many you have. And then when you get done with that, you're going to add them all up together. And that'll give you the, so once you add all those together, that's going to give you the average atomic mass. All right. Anybody need a second to write this down? Everybody's good? So I think I asked too many questions too fast. So is that everybody's good or everybody needs a minute? Yes, for the abundance, you're going to move the decimal place. Need time. Okay, cool. I'll give you a second. So for the abundance, you're going to take, they're going to give you, most likely, they're going to give you percentage like 89%. And then you're going to turn it into a decimal. You just take whatever percent they give you and divide by 100. But when you put it in your calculator, don't use the percent sign. You're just going to put in 89 divided by 100, and that's going to give you 0.89. The other option is just to take the decimal and move it 2 places this way. So that's how you get the fraction. Yes, I can do one more example. Let's see. Arif, you have a question.
Yes, Professor. I want to know, is it going to be different atoms, or is it going to be one atom, 3 different masses, 3 different abundance? So
it's going to be one element,
okay,
with 3 different masses, or however many masses there are, depending on how. If it's an element that has 3 isotopes, then you'll get 3 masses and 3 abundances. If it's an element that has 5 isotopes, you'll get 5 masses and 5 abundances.
All right, thank you.
You're welcome. For that one, Akash, I'm not sure I have enough time for that one this morning, but I can go over it on Friday if you like. Or if you need help on it, you can send me an email and I can help you on it via email. Or you can stop by during office hours too. No, not necessarily. Sometimes you have 4 isotopes, sometimes you have 3, sometimes you only have 2. It really just depends on the element. All right, so one more example, and then we're going to move on to stoichiometry, so don't run out of time. We'll do sample exercise 2.4. Starts on page 61 and goes to page 62. So this is the isotopes of strontium. So we have strontium 84, strontium 86, strontium 87, strontium 88. The masses of these are 83.9134 and then 85.9092, 86.9089, and 87.9056. Then you get the percent abundance. And that's 0.557%, 9.857%, 7.002%, and 82.584%. Most of it is strontium 88. So the atomic mass should be closer to 88 than it is 87, 86, or 84. So what you're going to do is you're going to take all of these and you're going to convert them to decimals. Right? So now that they're decimals, you can just kind of ignore the percent sign. I'm going to draw a line to make it where you can see these a little easier. Right? Now I'm going to multiply them together. And in this case, the x actually just means multiply. That's not a variable here. So you're going to multiply those together. And then once you multiply them together, just to save time, I'm not going to work out the whole thing, but the answer is in the textbook. So you'll get an answer that's a number, an answer that's a number, an answer that's a number, an answer that's a number. So you're going to take all four of these numbers. You're going to add them together. That's going to give you the average atomic mass. All right? Anybody need a second? All right, cool. All right, so let's move on to converting. Well, first we want to talk about the molar mass of something. So if you look at the periodic table, pull up a periodic table in a separate window and look at the periodic table. Make sure it has the atomic number and the atomic mass. So for example, beryllium is atomic number 4 and its mass is 9.012. Now, if you have one beryllium atom, technically it's 9.012 atomic mass units. If you have a mole of those units, then that would be 9.012 grams in 1 mole. So whatever the atomic mass is, that's going to be given to you as grams per mole. Talking about just one atom, like 1 cobalt or something, it's just whatever the atomic mass is, and the units are atomic mass units, which are given by a U. Generally, that's not terribly useful. What we use most often is we use it in the form of atomic mass units. No, in the form of grams per mole. I don't know why I said that. In the form of grams per mole. So let's say we have 2 moles of beryllium. And when I write this, make sure that you put what element you have, because as we move on a little further into the semester, we're going to be converting from one type of element to another. And even in this one, we may be converting from one to another. So make sure you put down what it is so that you're canceling out the right stuff. All right. So I need to have moles of beryllium on bottom, so they'll cancel. One on top, one on bottom cancels. And the atomic mass is right here. And that's going to give me, moles are going to cancel, and that's going to give me grams of beryllium in 2 moles. Anybody have a calculator handy? Let's see. All right, go ahead and plug it into your calculator. Let's see what we get. Yes, 18.024. Awesome. All right, and we can do it the opposite direction. Let me change colors. I'll go to orange. We could go, let's say it told us that we have 98 grams of beryllium. We can go from grams to moles, using the same thing, the atomic mass, only this time, since I have grams of beryllium here, the grams go on bottom. All right, grams of beryllium cancel. Now this time you're going to multiply across the top, so that'd be 98 times 1 equals 98, and then multiply across the bottom, and in this case we only have one number, so that'd be 9.012, and then plug that in the calculator, and that gives us 10.874 moles of beryllium. All right, so that's grams to moles and moles to grams. Now we can get more complicated than that. You should follow significant figures. I didn't. So this one should have just had one significant figure, and this one would have had two. But on the tests, this part should be pretty clear without having to worry too much about that. Yes, so this counts, and because this is an average atomic mass, the 9.012 counts. The 1 mole doesn't, because it's exactly 1 mole. All right, so let's make it, let's look at something else. Let's look at a compound. Let's look at carbon dioxide. So looking at this, how many atoms of carbon do I have? In this, yeah, just 1. And how many oxygen? Correct. So if I had a mole of these molecules, then that would tell me that I have how many moles of carbon? In this molecule. Yeah, 1. And then I would have 2 moles of oxygen. All right? So you can take the subscripts and figure out how many moles of carbon atoms there are, or how many moles of oxygen atoms there are. Yes. Yep, actually that's just about what I'm going to do. So let's start with grams. Let's say we have 82 grams of carbon dioxide. And I want to know how many moles of oxygen that is. And then once I figure out how many moles of oxygen, I want to know how many atoms of oxygen. All right. So I'm going to start with the 82 grams. That's okay. All right, so 82 grams. We're going to go first grams to moles. Usually the first thing you're going to do is either grams to moles or moles to grams. So we're going to use the atomic mass of carbon dioxide. Now, if you look on the periodic table, there's no atomic mass of carbon dioxide. What you have to do is you have to add up the masses. So carbon is 12.01, and I have 1 carbon atom, and oxygen is, well, they have 16 here. All right, so that's basically 32 plus 12, and my calculator won't work. Okay. Oh, cool, you guys got it. So it's 44 grams per mole. And that's how we figure out the atomic mass of the molecule. So that's 44 grams of carbon dioxide per 1 mole of carbon dioxide. Now, if I have 1 mole of carbon dioxide, we determined earlier that we have 2 moles of oxygen in 1 mole of carbon dioxide. So that's going to give us moles of oxygen. Anybody know how many moles that is? So that'll be 82 times 2, and then 44 times 1. So that's going to be what? 164 divided by 44. Yep. So that's what I got. All right. Now we're going to go from moles of oxygen to atoms of oxygen. What are we going to use to do that? Let's see. Well, it depends. Most of the time you can round it. Like even in this periodic table I'm looking at, they rounded oxygen because oxygen's 15.9997 and they rounded to 16. So yeah, they round, you can round. Yeah, Avogadro's number. Excellent. It's very important to put parentheses around Avogadro's number. If you don't, you'll get a weird number a lot of times. Okay, that's a good question. Okay, so we took the grams that were given to us of carbon dioxide, and then we took the molar mass of carbon dioxide, which we calculated up here, and then we know that in 1 mole of carbon dioxide, we have 2 moles of oxygen. And that's just because there's a subscript of 2 for the oxygen. And so we're going to multiply 82 times 1 times 2. So that gives us 144. No, not 144. 164. And then on the bottom, it's 44 times 1. So we divide by 44. And we put it in the calculator, and we get 3.73 moles. All right. So I got about 6 minutes. So I want to do another example. Does anybody need a second on this one? No? Okay. All right. So let's do atoms to grams. Let's say we have 1.87 times 10 to the 21 atoms of, instead of atoms, let's do molecules, because we haven't done molecules yet. Molecules of, or formula, actually it should be formula units. Of magnesium hydroxide. All right. So I want to know in the end, how many moles of hydrogen do I have? All right. So we got 1.87 times 10 to the 21 formula units of magnesium hydroxide. Formula units are for ionic compounds and molecules are for covalent compounds, but that's the only difference. All right, so we're going to go from formula units to moles. We're going to use Avogadro's number. 23rd or 10 to the 22? 10 to the 23rd. Formula units. All right. And so this is going to give us moles of magnesium hydroxide. Somebody really quickly take this number here, make sure you put parentheses around it, and divide it by Avogadro's number. And that's going to give us moles of magnesium hydroxide. While you're doing that, I'm going to set up the next part of the problem. All right, 0.003 moles. And I'm not plugging these numbers into the calculator, so if you get a different number, just check and see whether your number's right or not. So, but this is the general format of how to do this. Okay, how many moles of hydrogen are in magnesium hydroxide, in 1 mole of magnesium hydroxide? 2. Excellent. All right. And so at this point, you just take 0.003 multiplied by 2, that would be 0.006 moles of hydrogen. All right. So it gives you some practice for these kind of problems in the homework. If you get stumped, you can go to Google and just type in tutorials for grams to moles or grams to molecules. And it'll give you some examples of that, so you can just kind of see what, like, how's the flow going there. Also, in your chemistry textbook, in the normal one, they do have little videos. They don't make them very obvious. They have little blue links on the left of the page. So if you see like a little blue link, it doesn't look like a link. Let me see what it says. When it has those. See if I can find one. Oh no, sorry, Samantha. All right. Well, that's all I've got for today. Stop by during office hours if you need anything. Yes. So the homework that's due tonight is the stuff that was due Sunday. And the stuff that was due tomorrow is now due this coming Sunday. But if you check out D2L, the dates should be on there for you. You're welcome.